Assalamualaikum, Chem-20. So this is a kind of a recap of what we did briefly in Chem-20. What we're going to focus on in this video primarily are acid-base calculations of pH and concentration. So just a couple of quick definition reminders to set the context here. When we're talking about acids and bases, there's two large governing theories that define these slightly differently, right? So you have the first school of thought, which would be known as Arrhenius's acid-base theory. And what this basically states is that acids and bases require H2O. Okay, I'm going to make this a little bit more visible here. Sorry. So we're going to acids and bases require H2O in order to donate or accept their protons. So let's just hold on here. So donate or accept their protons. Of course, it depends on whether it's an acid or a base, whether it's going to accept or donate. And I'm going to kind of draw a box here just so you know that this is going to govern everything here. And then you had what we call Bronsted-Lowry's acids and bases. So Bronsted and Lowry, two scientists that came together for this combined idea. And this was that H2O was no longer needed. And here, this gave rise to polyprotic. I'll make that word rise in case you're feeling, what is that? It's the word rise. Sometimes when we're trying to write quick, it's a bit hard to read. So it gives rise to polyprotic and amphiprotic entities. Okay, and they still run under the same general definition that bases must accept at least one proton, and then of course acids must donate at least one proton. There are other key, properties of acids and bases, and we're going to summarize them quickly here. So, key properties of acids and bases. And we'll begin with acids first. So one of the main properties of acids is that they donate, or you could say release, sort of a synonym in chemistry, H+ ions in solution. But according to Bronsted, it's not really about the H+ necessarily. According to Bronsted and Lowry, they release protons, and we're going to see when you get into university that under Lewis acids that makes sense, and stuff like Al3+ or aluminum nitrate is actually quite an acidic solution. So they donate, release H+ in solution, and of course the H+ that we refer to is really short form for the hydronium ion, which is H3O plus, right? So they are the same thing. H3O plus and H plus are the same thing. The other thing that acids tend to do is they tend to neutralize bases, which means that they're able to react quite vigorously. And actually, we're going to see that in an exothermic reaction. The other thing that acids are able to do is that they're able to react, we'll say vigorously, which means very violently and quickly, with metals, given that the type of acid we're dealing with is spontaneous, right? So react vigorously with metals, and of course, that will be if spontaneous. So something like HCl and copper solid are not spontaneous, right? So this wouldn't apply. Okay. Other common things that we know from acids, they turn all litmus, doesn't matter what kind we're using, blue, red, or neutral, all litmus paper red, and they all have a pH that is under 7. Okay, and it is important to note that we have something called strong acids, and then we have weak acids, and when we say strong acids, we're referring to the first 6 listed on page, I believe it's page 8 of your data booklet. So everything right before H3O plus. So strong acids are the first 6 listed on the data booklet. They fully ionize into solution. Now, in Chem-20 that didn't mean much, but in equilibrium that means a whole lot. If we take a strong acid, for example, like HCl, what we say is that it fully ionizes. Now in Chem-20 we just had you write the double arrows, right? But that didn't mean anything until this year. Full ionization looks like this, where HCl breaks into H plus and Cl minus. Okay, and of course the mechanism would be water, but as Bronsted says, it doesn't have to be the only mechanism. Sorry, I put H2O, but it should be H2O over here. So it's not the only thing, but that is the mechanism that we focus on. And so this single arrow here, okay, the single arrow means full ionization. But in equilibrium, it also has a meaning. In equilibrium, okay, so in equilibrium, it means quantitative. And I'm going to write that word in red. It's quantitative, and that means cannot be reversed. So it's one of those special types of reactions that can't go back and forth. And so that means that the percent yield of all the ionization reactions of the strong acids, percent yield is going to be between 99 and 100%. And what we're also going to write here is, put a starred note, because they ionize 100% or close to 100%, we can calculate pH values directly from concentrations okay, and this is because the acid concentration, since it fully ionizes, is going to be equal to the H plus concentration. Okay, now your weak acids they're a little bit different. So the weak acids is any acid after the first 6. And that includes hydronium, which people think that's kind of counterintuitive, and I agree, but remember that this is all based on what things actually do in solution, not what we think should always make sense, right? So any acid after the first 6. Okay, so these ones do not fully ionize. In fact, they have a lot of trouble ionizing, period. Okay, so do not fully ionize into solution. And so if I take a weak acid, for example, let's say I take hydrofluoric acid. Well, what it's going to do is we're going to write a double arrow, which in Chem-20 said that, or meant that it didn't fully ionize. And in Chem-30, we're going to go a little deeper to say that it's in a state of dynamic equilibrium. But this is how it reacts in solution. And that double arrow means that reaction is reversible, and only weak acids can have these reactions reversed. The other thing that we're going to understand is that, and I'm going to erase that yellow line here so that we can have some room to write it, is that the mechanism, right, the ionization capacity or capability of these acids, it's going to reach the forward reaction with a percent yield of less than 50%. So percent yield is less than 50. And what that basically means is that the acid concentration is actually going to be more than, we wrote greater than, but it should be more than your H plus concentration. That's because it doesn't fully ionize. And so with these ones, we cannot calculate pH directly from concentrations. Okay, and we have to deal with these guys a little differently. We've never dealt with them before in terms of pH calculations in Chem-20, but we will deal with them in Chem-30 and show you how that works. However, what I want to say is that both of these, regardless of them being weak or strong, are still going to possess all of these properties over here, right? Just the weak acids are going to be to a lesser extent. So weak and strong possess these properties. Now, why is it a negative log as opposed to just using a normal scale and still keeping the tenfold? Honestly, that's one of the things that we're never actually going to understand because this work was incomplete. the original scientist Sorensen that discovered, or you could say formulated these pH calculations, we're not exactly sure why he used the negative log as opposed to a regular logarithmic function. But what we can say is that the function works and it is very good at predicting acid-base behavior. Now, what does pH actually stand for? Something called the power of hydrogen. Because you're dealing with volumes of solution where there are incredibly large numbers of hydronium ions or hydroxide ions, kind of navigating the solution, it makes sense to treat them in powers of or to the exponent of, as opposed to counting every single individual hydronium molecule or hydroxide molecule. So we don't know why it's negative, but we do know why we use a logarithmic function. Let's get to some calculations and see how this actually works. So here's the pH scale. 7, of course, would be anything that is considered to be neutral. And the way it works, if we can recall, is that anything past this line is basic. And then anything that goes to the left of that neutral line would be considered acidic. And that the difference between each of these, so 1 and 2 is times 10, 2 and 3 times 10, etc. And what we want to also understand, to kind of add on to this, is that as we move to the left, that means that your H plus increases, right? The solutions are more acidic. But as you move towards the right of the neutral sign, this means that your H plus decreases. At the same time, I'm going to write this underneath here. I'm going to erase this. Actually, I won't erase it. I'll leave it here. When it comes to the OH, because the OH can also be read from this as well, as we move towards the left, as your H plus increases, your OH minus decreases. And as your H plus decreases, that means that your OH minus increases. And what we're saying here is that your H plus and OH minus are inversely proportional. By that same token, we can also say the same thing between the two entities of pH and POH, where pH, which measures the H plus logarithmic concentration, and POH represents the OH minus logarithmic calculations. pH and POH are also inversely proportional. So the summary of all, these relationships that we were talking about previously can be, given in this box of formulas here, where we can find the pH of a known solution, which is the negative log of the H2O plus. Now remember that these are concentrations, okay, and they have to be in moles per liter. So not moles, but moles per liter. And the same is true with the hydroxide over here as well. So this is concentrations, and this is in moles per liter. And so to find the pH, I go negative log H3O plus. If I wanted to find the H3O plus and I'm given a pH value, well, again, the inverse of an exponential function or of a logarithmic function is an exponent or an exponential function. So we just go 10 to the exponent, whatever the pH is, but it has to be the negative. Don't forget the negative, okay? So don't forget negative. Okay, and then the same is true when it comes to the OH. And then we have probably one of the most used formulas here, which is the pH plus pOH is equal to 14. And now that we're in grade 12, or some of us anyway, they would have done Math 30 by now. And one of the rules in logarithmic functions is that, and you know, this is a good little math, you know, preview for those that are going to go into Math 30, is that log A, so log with base A plus log of base B is equal to log A times B. And so what we're basically saying with this formula here is that the log of the acid plus the log of the base, the log function of the base, is equal to, well, the entire scale of pH and pOH, which is 14. So combined, they always have to equal 14. And so this is where this actually comes from. So let's get into actually using these formulas here. The first thing that we're going to do is we're going to find the pH of a solution given a concentration. So we look at this one here. It says, what is the hydronium concentration of a substance with a pH of 3.78? Well, hydronium refers to, remember, that's H3O plus. And when we look back at our formulas, we see that to find the hydronium concentration, it's H3O plus is equal to 10 to the negative pH. So all we have to do is go H3O plus is equal to 10 to the negative 3.78. And when we plug that in our calculator, we end up getting a hydronium concentration of about 1.66 times 10 to the negative 4 moles per liter, and that's our first one. Now, let's move on to our second example. If a substance has a hydroxide concentration of 2.57 times 10 to the negative 11 moles per liter, what's the pOH of the substance? Now, as we listed previously, the pOH, or the power of hydroxide, is equal to the negative log OH minus. Since we already have the OH minus, all we have to do here is plug it in directly, which is 2.57 times 10 to the negative 11, and that's moles per liter. And the value that we end up getting is about 10.59. Now remember that pH and pOH don't have any units because we're describing very specific substances in concentration. So we don't have to include units. This is the power of hydrogen or hydroxide available in this solution. Now let's move on to a little bit more complicated examples. So when we look at this one over here, there's going to be a bit of or some extra steps. Okay, so we're going to scroll up here. Alrighty, so it says find the pH of a solution that contains 3.25 grams of H2SO4 dissolved into 2.75 liters of solution. So first, remember, okay, and I'll write this over here, that your pH and pOH require concentration. So to have grams or molar amounts, it's useless to us. So we're going to take this 3.25 grams and the 2.75 liters and get the concentration. First thing that'll do is convert this to moles. So we'll go for the moles of H2SO4, we're going to go 3.25 grams divided by the molar mass, which is about 98 grams per mole. And then that would leave us with about 0.033 moles of H2SO4. For those that prefer to do it the unit analysis method, I'll do it kind of quickly over here. We'll do it in yellow, but it's really not that important how you do this. So my unit analysis kind of looks like this: 3.25 grams H2SO4 multiplied by 1 mole per 98 grams. And then when we cross this, we would still get the same thing, 0.033 moles of H2SO4. Again, do the way you're most comfortable with it. It's going to be the same regardless. Okay, now that we have the moles, we're going to go C is equal to N over V. We're going to get the concentration. So this is kind of like the first step. This could be the second concentration. And that's going to be equal to 0.033 moles per liter of H2SO4 divided by 2.75 liters. And then that gives us the concentration of 0.0121 moles per liter of H2SO4. Now, since this is a strong acid, you would see that it's in the top 6. Then we can say that your H2SO4 concentration is equal to the H3O plus concentration that it would yield, because it ionizes 100%. So what we can do now that we have the concentration, the final step is just to plug it directly in. So we're going to go pH is equal to negative log H3O plus, which is then going to equal to negative log 0.0121 moles per liter. And then finally, the pH of this solution would be about 1.62. Okay, so a little bit more complicated, more steps, but the idea is still the same. And we're going to conclude with a final, more complicated one over here. So it says find the pH of a 0.000841 moles per liter solution of sodium hydroxide. Okay, the thing is, remember that sodium hydroxide, because of the OH, that's a strong base, right? Anything with an OH is a strong base. And so this releases OH ions. It does not release H+. So the path that we're going to have to follow is this. We're going to have to go from the POH of NaOH to the pH using the combined formula of pH plus POH is equal to 14. So we're going to go, first let's get the POH. Now we have the concentration, right? And remember, since it's a strong base, the NaOH concentration in moles per liter is going to be equal to the hydroxide concentration in moles per liter because it's strong. So we can plug in our concentration directly into the POH formula, which is negative log OH minus, which is going to be negative log 0.000841. And when we calculate that, that would give us a POH value of about 3.08. And again, don't forget to put the negative log. Now to get the pH we're going to go pH plus POH is equal to 14. We'll move the we'll move the POH to the other side so that our equation becomes pH is equal to 14 minus POH. And then when we plug it all in, we can easily get the pH of our basic solution. And that would be 14 minus 3.08. And that gives us a total pH of about 10.92.